to Educator.com. In today's lesson, we'll be talking about solving systems of equations algebraically. In the previous lesson, we talked about solving systems of equations by graphing. However, that method has some limitations. Therefore, we're going to talk about a few other methods of solving. And this is some review from Algebra 1. So again, if you need more detail, more review on these concepts, check out our Educator.com Algebra 1 series. First, we're going to review solving by substitution. First, jotting down a system of equations, 2x plus 3y equals 12. And the second equation in the system is x plus 4y equals 1. In this method, you're going to solve one equation for one variable in terms of the other variable. Then, substitute the expression for the variable in the other equation. Let's look at what this means. First step, solve one equation for one variable in terms of the other one. The easiest thing to do is to find a situation where you have a variable that has a coefficient of 1, and I have that right here. So then I can solve for x in terms of y pretty easily. So x plus 4y equals 1. So I'm going to solve for x in terms of y. This gives me x equals negative 4y plus 1. The second step is to substitute this expression for the variable in the other equation. So I'm going to substitute negative 4y plus 1 for x in the first equation. And that's going to create an equation that has only one variable, and then I'll be able to solve that. So it's important that you go back into the other equation to substitute in. Okay, so this is going to give me 2 times negative 4y plus 1 plus 3y equals 12. Then I can just solve for y. So 2 times negative 4y, that's negative 8y, plus 2 times 1, that's just 2, plus 3y equals 12. Combining like terms, negative 8y and 3y gives me negative 5y, plus 2 equals 12. Subtracting 2 from both sides to get negative 5y equals 10. Dividing both sides by negative 5, I get y equals negative 2. Once I have one variable solved, I can easily solve for the other. So I just go back to either one of these, and this one's easier to work with, and I'm going to substitute in, I'm going to let y equal negative 2. X plus 4 times negative 2 equals 1. So this is going to give me x plus negative 8 equals 1, or x minus 8 equals 1. Adding 8 to both sides, I get x equals 9. So here, y equals negative 2 and x equals 9. This method of substitution works really well when the coefficient of one of the variables is 1. So use this when, use substitution when a variable in one of the equations has a coefficient of 1. Okay. So again, we looked at the system of equations, saw that this variable had a coefficient of 1, then solved for this variable x in terms of the other variable y to get x equals negative 4y plus 1. And then I went ahead and I substituted this for x in the other equation. That gave me one equation with one variable, and I can solve for y. Once you have y, you can substitute that value into either equation and then solve for x. The second method is solving by elimination. In elimination, you add or subtract the two equations to eliminate one of the variables from the resulting equation. And this system works well when you have variables, either the two x's or the two y's, that have either the same coefficient or opposite coefficients. By opposite coefficients, I mean the same number but with opposite signs, such as 2 and negative 2, or 3 and negative 3. For example, if you were asked to solve this system, you look and see that there's no variable with a coefficient of 1. Therefore, substitution is not the ideal. It's not the easiest way to go. But what you see is that you have one variable, you have y, that has the same coefficient. So adding is certainly not going to help me. If I add these together, I'll get 6x plus 10y equals 8. What I need to do is subtract, because my goal is to get one variable to drop out. So I'm going to subtract this second equation from the first. And just to help me keep my signs straight, I rewrite that as adding the opposite. So I'm adding negative 4x, negative 5y, and negative 3. Okay, this is going to give me 2x minus 4x is negative 2x. Y's are going to drop out. 5y minus 5y gives me 0. So I can write plus 0, but they just drop out. And then 5 minus 3 equals 2. So this is negative 2x equals 2. I can easily solve for x, and x equals negative 1. Once I have one variable, I can go to either original equation and then substitute in order to solve for the other variable. So I know that x equals negative 1, so I'm going to substitute that up here. Add 2 to both sides. That's going to give me 5y equals 7. And divide both sides by 5 to get y equals 7/5. So solving by elimination, I was able to come up with the solution that x equals negative 1 and y equals 7/5 will satisfy both of these equations. Again, this works well. Use elimination when variables, the same variable, meaning both x's or both y's, have the same or opposite coefficients. So the same coefficient but opposite signs. Okay, sometimes you look and you see that the variables, there's no variable with a coefficient of 1, and then you say, okay, I'll use elimination, but then you realize that none of the variables have the same or opposite coefficients. In that case, you can still use elimination, but you're going to have to take an extra step before you do the elimination. And the extra step is to multiply one or both equations so that one of the variables has the same or opposite coefficient in the two new equations. So your goal is to create a situation where one of the variables has the same or opposite coefficients. Then you just use elimination as we did previously. If you had a system of equations, 5x plus 4y equals 1, and 6x plus 3y equals 3, you see that neither of these has a variable with a coefficient of 1, and neither set of variables has the same or opposite coefficients. But if I look at these two, 4y and 3y, the least common multiple is 12. So what I want to do is multiply each of these by something in order to end up with a coefficient of 12 in front of the y. Sometimes you'll be lucky and all you'll have to do is multiply one of the equations by a number to get the opposite or same coefficient. Other times like this, you're going to have to multiply both. So for the first equation, I'm going to multiply by 3. And this is going to give me 15x plus 12y equals 3. Okay, second equation, I'm going to multiply by 4. So this is going to give me 4 times 6x is 24x plus 12y equals 12. Okay, I now see that I have the same coefficient for y. So rewriting this over here, I need to subtract. So I'm going to subtract the second equation from the first. And to keep everything straight, I like to go about this by adding the opposite to make sure that I keep my signs straight. So I'm going to add negative 24x minus 12y. And then that's going to be a negative 12. Okay, negative 24x minus 12y minus 12. Add these together. So I get 15 minus 24x. That's going to give me negative 9x. The y's drop out. And then I have 3 minus 12. That's negative 9. Divide both sides by negative 9 to get x equals 1. From here, I substitute back. I'll choose this top equation. 5x plus 4y equals 1. And I know that x equals 1. This is 5 times 1 plus 4y equals 1. So that's 5 plus 4y equals 1. Or 4y equals negative 4. So y equals negative 1. So x equals 1, y equals negative 1. Again, this is just the first step in elimination. And you use it in a situation like this where you want to use elimination, but you don't already have a set of variables with the same or opposite coefficients. So you figure out what the least common multiple is and multiply one or both equations in order to achieve that. From there, you just proceed as we did before, solving by eliminations. There's several different possibilities that can occur when you're solving systems of equations algebraically. Usually, in the problems that you'll see, what will happen is what just happened previously that I showed you, where you'll end up with a value for x and a value for y that satisfies both equations. However, there are times when that doesn't occur. You can be going along, doing substitution, doing elimination, and things are going fine, and then you end up with something like this. C equals D. Your variables drop out, and you end up with a constant, and an equation that's saying a constant is equal to a different constant. For example, 4 equals 5. Well, that's not true. So when you see this, this is an equation that is never true. And what this tells me is that the system of equations is inconsistent. So this is a situation where there's no solution. So if you start seeing a situation where the constants drop out, and then you see something like 4 equals 5 or 9 equals 10, something that is not true, then you know you have an inconsistent system. The other possibility is that you could have a system that is dependent or always true. In that case, you're going along, you're doing elimination, you're doing substitution, and then you see that you end up with variables dropping out and a constant that equals a constant, the same constant. For example, 3 equals 3. Well, that is always true. So if you end up with an equation, the sum or difference of the two equations, the system of equations, that is always true, this system is dependent and it has an infinite number of solutions. Recall when we were solving systems of equations by graphing, this is analogous to the situation where you'd end up with the same line. So if two equations, a system of equations, you graph both equations, you find out that there's the same line, well then there's an infinite number of solutions. It's all points along those lines. Here, no solution would be like parallel lines, where they never intersect, there's no solution to that system. Okay, first example is solve algebraically for the system of equations. As soon as I see that, okay, I have variables, or even one variable with a coefficient of 1, I recognize that substitution would be a really good method to use. So use substitution when a variable has a coefficient of 1. So I'm going to solve for x in terms of y. So x plus y equals 5. So x equals 5 minus y. Now, I've solved for x in terms of y, and now I'm going to substitute this value into the other equation. 2x plus 3y equals 13. So I'm going to substitute this expression for x. So 2 times 5 minus y plus 3y equals 13, or 10 minus 2y plus 3y equals 13. This is 10 plus y equals 13. Then subtract 10 from both sides to get y equals 3. Once I have this, I can plug y into this simple equation up here. So x plus y equals 5. Substitute in, let y equal 3. And I get x equals 2. And this is very easy to check. You can see that if x is 2 and y is 3, this equation holds true. And you could do the same, plug it back into that first equation, put these values in for x and y, and just verify that these solutions are correct. Okay, so again, solving by substitution because you had a situation where you had a variable, or actually two variables with a coefficient of 1. So that's the easiest method to use. Okay, here I'm solving this system of equations algebraically, and I don't have any variables with a coefficient of 1, so I'm not going to use substitution. But if I look, I have variables, I have y, that have the opposite coefficient, -3 and 3. What that means is that if I add these equations, the y's are going to drop out. Then I can just solve for x. Rewriting this right here and adding. So I'm going to add these two. 2x plus 4x, that gives me 6x. Y's drop out, -3y plus 3y, well that's 0. And then 0 plus 9 is 9. So I'm going to divide both sides by 6. This is going to give me 9/6, and that simplifies to 3/2. So I have x equals 3/2. I'm going to pick either one. I'll go ahead and pick the top one. 2x minus 3y equals 0. And let x equal 3/2. Substitute that for x. The 2's cancel out. This gives me 3 minus 3y equals 0. Or -3y equals -3. If I divide both sides of the equation by -3, I'll get y equals 1. So solution, x equals 3/2, y equals 1. Again, I could always check these solutions by substituting the values in here and making sure that this equation holds true. And this was a perfect setup to use elimination because I already had variables that had the opposite coefficient. I simply added these equations together. The y dropped out, allowing me to solve for x, and then substitute 3/2 in for x. Okay, solve algebraically. Again, no variables with a coefficient of 1, so I'm going to go to elimination. But these do not have the same or opposite variables, and the y's do not have the same or opposite variables. So this time, I'm going to need to use that extra step. I'm going to need to use multiplication in order to create a situation where I have variables with the same or opposite coefficient. And I see that if I multiply the top equation by 3, I'll get 6x. And if I multiply the bottom equation by 2, I'll get 6x. So I'm going to go ahead and do that. Multiply the top equation by 3. So that's going to give me 3 times 2x minus 3y equals -16. And this comes out to 3 times 2x is 6x. 3 times -3, that's -9y. And 3 times -16 is -48. Second equation, I'm going to multiply by 2. So 2 times 3x plus 5y equals 14. Okay, 2 times 3x gives me 6x. 2 times 5y is 10y. And 2 times 14 is 28. I have the same coefficient here, so what I need to do is actually subtract. So I'm going to subtract. And again, I'm going to convert this so that I'm adding the opposite. So rewriting the top equation the same and the bottom as adding the opposite. So adding -6x minus 10y minus 28. Okay, when I do that, the 6x's drop out. And that's going to give me negative 19y equals negative 48, negative 28 comes out to negative 76. Divide both sides by negative 19, and negative 76 divided by negative 19 actually equals 4, so it divided very nice and evenly. So I ended up with y equals 4. Now that I have that, I'm going to substitute y equals 4 into either equation. I'm going to choose the top one. So 2x minus 3y equals negative 16. Let y equal 4. So 2x minus 3 times 4 equals negative 16. Or 2x minus 12 equals negative 16. Add 12 to both sides to get 2x equals negative 4. And divide both sides by 2 to get x equals negative 2. So the solution is that x equals negative 2 and y equals 4. So when I looked at this, I saw that I could use elimination if I got the x's to have the opposite coefficient by multiplying the top equation by 3 to give me 6x and the bottom equation by 2 to give me 6x here as well. So I did that. And then these had the same coefficient, so I subtracted and solved for y. Once I had a value for y, I substituted that value into one of the equations and then solved for x to get the solution. Here I have 2x plus 3y equals 8 and negative 4x minus 6y equals negative 16. Since there's no variable with a coefficient of 1, I'm going to use elimination. But again, I'm going to have to do a little work to get the opposite coefficients. And I see here that all I have to do is multiply the top by 2, and that'll give me 4x. So that's opposite coefficients. I don't have to do anything to the bottom equation. So that's 2 times 2x plus 3y equals 8. And this is going to give me 4x plus 6y equals 16. So that's the opposite coefficient, so I'm going to add this new equation and this equation. So plus negative 4x minus 6y minus 16. And you may have already realized that each one of these terms is opposite. And so here's what's going to happen. 4x minus 4x is 0. 6y minus 6y is 0. 16 minus 16 is 0. So I end up with 0 equals 0. And I didn't make any mistakes. I did everything correctly, but then all my variables went away. And what this tells me is that I have a dependent system and it has an infinite number of solutions. If I were to graph this, I would see that I have an infinite number of solutions, that these are intersecting at every point along a line. So we call this a dependent system. If I would have been going along and all the variables dropped out and then I got something that wasn't true, like 4 equals 2 or 4 equals 0, then I would have a situation where it's an inconsistent system and there's no solutions. But here, this is always true, so I have an infinite number of solutions. So today we covered solving systems of equations algebraically, and that concludes today's lesson for Educator.com. I'll see you again.